Galaxy collisions are the universe's greatest construction projects. The word collision makes you picture cosmic destruction. Most people imagine stars smashing into each other, explosions, chaos. The universe's most violent demolition project. Tonight we're discovering why the opposite happens. We'll trace the evidence that shocks astronomers. Before we explore these cosmic builders, drop a comment about what you think happens when galaxies meet. If you enjoy these space discoveries, consider subscribing. Scientists created the most detailed galaxy collision simulations ever built. These are computer models that predict what happens when two galaxies meet. They expected to witness cosmic carnage. What they found changed everything about our understanding. In a collision between two galaxies, stars don't crash into each other. They rearrange through what astronomers call gravitational choreography. That means gravity guides their movement like an invisible conductor. The number of actual stellar collisions rounds to zero. Picture two massive swarms of fireflies approaching in darkness. As they merge, individual fireflies weave between empty spaces. They reorganize into new patterns without touching. This happens because of scale. Stars are incredibly tiny compared to the distances between them. Our nearest stellar neighbor sits farther away than you can imagine. When galaxies merge, stars navigate vast emptiness with precision. Gravity reshapes their paths. They settle into new neighborhoods, but they keep burning peacefully throughout the entire process. The Andromeda Galaxy approaches our Milky Way right now. That's our nearest major galactic neighbor. It moves toward us faster than anything humans have ever built. This neighbor will merge with our galaxy in several billion years. Most people expect this collision to destroy both galaxies. Astronomers calculated the opposite outcome. Our combined galaxy will contain far more stars than either original possessed. Andromeda brings roughly 1 trillion stars to this merger. That's 1,000 billion individual suns. Our galaxy contributes several hundred billion more. But here's what makes this truly remarkable. The gravitational interaction triggers massive episodes of star birth. Gas clouds throughout both galaxies get squeezed together. When gas compresses beyond a certain point, it ignites into new stars. This process creates what scientists call a starburst. That means the rate of star formation explodes to many times normal levels. Our galaxy emerges from this collision bigger and more star-rich than before. The universe builds its largest structures through these seemingly violent encounters. The distances between stars make collisions virtually impossible. Even in the densest parts of galaxies, stars remain separated by enormous gaps of empty space. Imagine shrinking our sun down to the size of a golf ball. The nearest star would be another golf ball sitting on the opposite coast. That's the scale we're dealing with in space. When two galaxies containing hundreds of billions of these widely separated stars pass through each other, the math is startling. The probability of any two stars actually colliding approaches zero. Most of space consists of absolutely nothing. Stars occupy less than 1/billionth of the total galactic volume. They're like specks of dust scattered through an enormous empty cathedral. During a galactic merger, stars sail past each other through this vast emptiness. Gravity bends their paths. It changes their speeds. It reorganizes their orbits completely. But the stars themselves never make contact. This mathematical reality transforms our entire understanding of what galaxy collisions actually mean. Gravity doesn't just prevent collisions during galactic mergers. It actively reshuffles stars into completely new arrangements. This process exchanges orbital energy between different stellar populations. Think of it like a cosmic mixing bowl. Stars that once lived in the outer regions of one galaxy can end up near the center of the merged system. Inner stars get flung to the outskirts. The gravitational interaction redistributes everything. This energy exchange happens through what physicists call gravitational encounters. When stars pass near each other, they trade momentum and energy. One star speeds up while another slows down. Over millions of these encounters, the entire stellar population gets thoroughly mixed. The original spiral patterns of both galaxies disappear. The stars settle into a new configuration that's completely different from either parent galaxy. Scientists measure this process in computer simulations that track every single star. They watch as organized spiral structures dissolve into smooth, elliptical shapes. The final result creates an entirely new type of galaxy with its own unique stellar distribution. Galaxy collisions create massive shock waves that ripple through interstellar space. These aren't sound waves, but pressure waves that compress the gas between stars. This compression triggers the most dramatic episodes of star formation in the universe. Normal star birth happens slowly and sporadically. Gas clouds gradually collapse under their own gravity over millions of years. The process creates just a few new stars at a time. Collision shock waves change this completely. They squeeze vast regions of gas simultaneously. The compression pushes gas density far beyond the normal threshold for star formation. Picture squeezing a sponge filled with water. The liquid gets forced out rapidly and dramatically. Shock waves do something similar to galactic gas clouds. These compressed regions ignite into what astronomers call stellar nurseries. Hundreds or thousands of new stars can form in the same region during relatively short time periods. The shock wave effect explains why merging galaxies often appear much brighter than normal galaxies. They're blazing with the light of countless newly born stars. Tidal forces during galaxy collisions stretch and deform both participants. These are the same gravitational forces that create ocean tides on Earth, but operating on a galactic scale. Each galaxy pulls on different parts of its neighbor with varying strength. The side closer to the approaching galaxy feels stronger gravitational pull than the far side. This difference in force creates a stretching effect. Spiral arms get distorted first. The elegant curved structures that define spiral galaxies begin to warp and twist. Some sections get pulled away from the main galaxy entirely. These distorted features create spectacular tidal tails. Long streams of stars stretch between the two merging galaxies like cosmic bridges. Astronomers have photographed many examples of these dramatic structures. The tidal reshaping doesn't just destroy the original spiral patterns. It also triggers new spiral wave formation. The gravitational disturbances can actually regenerate spiral arms in different locations. This process demonstrates how galaxy collisions both demolish and create structure simultaneously. The final merged galaxy becomes larger and more massive than either original participant. This outcome contradicts every intuitive expectation about collisions and destruction. When the merger process completes, astronomers observe a single elliptical galaxy. These are smooth, football-shaped systems without spiral structure. They represent some of the most massive galaxies in the universe. The combined mass exceeds simple addition of the two original galaxies. This happens because the merger triggers enormous amounts of new star formation. All those newly created stars add to the total mass. The gravitational binding also becomes much stronger. The merged galaxy holds together more tightly than either original system. This creates long-term stability that can persist for billions of years. Elliptical galaxies formed through mergers often become the dominant members of galaxy clusters. They grow into cosmic giants that dwarf their spiral galaxy ancestors. The universe builds its most impressive structures through this apparent destruction process. Galaxy mergers trigger what astronomers call starburst events. These are periods when star formation rates increase by factors of 10 or even 100 compared to normal levels. The starburst phenomenon happens when collision shock waves compress enormous amounts of gas simultaneously. Instead of the usual slow, steady star birth, entire regions ignite at once. These events create some of the brightest objects visible across cosmic distances. Starburst galaxies can outshine normal galaxies by enormous factors. They become cosmic beacons visible billions of light years away. The intense star formation doesn't last forever. The available gas gets consumed relatively quickly, but during the peak starburst period, these galaxies produce stars at truly extraordinary rates. Some starburst galaxies create more new stars in a few million years than the Milky Way produces in several billion years. This represents one of the most dramatic processes in the entire universe. The starburst effect transforms sleepy, normal galaxies into blazing stellar factories. Galaxy collisions funnel enormous amounts of matter toward the central black holes of both participants. This feeding process transforms quiet black holes into some of the most energetic objects in the universe. Each galaxy contains a supermassive black hole at its center. These are objects millions of times more massive than our Sun. Under normal circumstances, they consume matter slowly and quietly. During a merger, gravitational forces channel gas and stars directly toward these central monsters. The black holes begin feeding at rates far beyond anything they experience in isolated galaxies. As matter spirals into a black hole, it heats up and glows brilliantly. The feeding black hole becomes what astronomers call an active galactic nucleus. These objects can outshine the entire rest of their host galaxy. The energy output from active galactic nuclei can be detected across enormous distances. They become among the most luminous objects in the observable universe. This black hole activation represents another way that galaxy collisions create rather than destroy cosmic phenomena. Galaxy collisions accelerate evolutionary processes that would normally require billions of years. They compress eons of gradual development into relatively brief cosmic episodes. Under normal circumstances, galaxies evolve very slowly. Spiral patterns form and dissolve over hundreds of millions of years. Star formation rates change gradually. The overall structure remains relatively stable for enormous time periods. Mergers change this timeline completely. Processes that would unfold over 5 to 10 billion years happen in just a few 100 million years instead. The collision forces rapid transformation from spiral to elliptical structure. It triggers massive star formation episodes. It activates central black holes. All these changes occur during a compressed time frame. Astronomers observe galaxies at various stages of this accelerated evolution. They can see the merger process happening in real time across different examples throughout the universe. This time compression effect allows the universe to build mature, massive galaxies much faster than gradual evolution would permit. Galaxy mergers represent the primary mechanism by which the universe constructs its largest structures. Small systems combine to form progressively larger and more complex arrangements. This process follows a pattern called hierarchical structure formation. The universe began with tiny density fluctuations. Gravity amplified these fluctuations over cosmic time. Small proto-galaxies formed first. These early systems contained just millions or billions of stars. They merged with neighbors to create progressively larger structures. Today's giant elliptical galaxies result from multiple merger episodes spanning billions of years. Each collision added mass and complexity to the growing structure. Galaxy clusters and superclusters also form through this same merging process. Individual galaxies combine into groups. Groups merge into clusters. Clusters connect through vast filamentary structures. The universe builds its architecture from the bottom up through countless collision and merger events. What appears destructive at small scales creates magnificent cosmic structures at larger scales. Stars almost never crash into each other during galaxy mergers. The distances between them exceed anything you can visualize on Earth. Consider our Sun as a tiny dot. The nearest star sits tens of thousands of times farther away than our Sun's own width. That's like placing two pinheads on opposite sides of a continent. Even in the densest star clusters, individual stars remain separated by enormous gulfs of empty space. A star's diameter measures just a few million miles, but the typical distance to its nearest neighbor spans trillions of miles. When two galaxies interpenetrate, stars weave through these vast gaps without ever coming close to contact. The scale difference makes physical collision extraordinarily unlikely. Galaxy mergers represent a gravitational reorganization, not a demolition derby. What happens when the overall gravitational field of a galaxy suddenly changes? Every star's orbit must adjust to the new conditions. This creates a massive redistribution of stellar populations throughout the merged system. Gravitational potential describes how strongly gravity pulls at any given location. Think of it like a landscape of invisible hills and valleys. Stars roll along paths determined by this gravitational terrain. During a merger, the gravitational potential gets completely rewritten. Deep valleys become shallow. Steep hills flatten out. New peaks and valleys form in different locations. Stars respond by finding new equilibrium orbits. Some migrate inward toward the galactic center. Others get flung to the outer regions. The entire stellar population shuffles into a completely different arrangement. This orbital redistribution process achieves a new gravitational balance that can remain stable for billions of years. Can you predict exactly where a star will end up after a galaxy collision? The mathematics of gravity makes this impossible beyond a certain point. This limitation stems from what physicists call the three-body problem. The three-body problem occurs when three massive objects interact gravitationally. Unlike the simple two-body case, three-body systems become chaotic and unpredictable. During galaxy mergers, every star feels gravitational pulls from countless other stars simultaneously. This creates an enormously complex version of the three-body problem involving billions of participants. Small differences in initial conditions get amplified into dramatically different outcomes. A star that starts just slightly closer to one region might end up in a completely different galactic neighborhood. This chaotic behavior actually increases the diversity of final stellar orbits. The unpredictability helps mix stellar populations more thoroughly than any orderly process could achieve. Galaxy collisions transform organized spiral patterns into the complex, mixed arrangements we observe in elliptical galaxies. More massive objects can behave differently than lighter ones during galaxy mergers. They experience something called dynamical friction that causes them to sink toward the galactic center. Dynamical friction works like moving through a crowded room. A large person bumps into more people and faces more resistance than a small person navigating the same crowd. More massive objects interact gravitationally with more surrounding stars as they move through space. These interactions gradually slow them down and reduce their orbital energy. Lower orbital energy means they settle into tighter orbits closer to the galactic center. Meanwhile, lighter stars maintain their higher energy orbits in the outer regions. This process creates what astronomers call mass segregation. Heavy stars concentrate toward the center, while light stars spread throughout the outer galaxy. The final result produces a galaxy with distinctly different stellar populations at different radial distances. How does a merged galaxy avoid flying apart or collapsing into itself? The answer lies in a fundamental physics principle called the virial theorem. This law governs the balance between gravitational energy and kinetic energy. The virial theorem states that gravitational potential energy and kinetic energy must maintain a specific mathematical relationship. For a stable system, the kinetic energy is about half the magnitude of the gravitational potential energy. Think of this like a cosmic budget that must always balance. If stars move too fast, they have excess kinetic energy and the galaxy expands. If they move too slowly, gravity wins and the system contracts. During galaxy mergers, gravitational interactions automatically adjust stellar velocities to maintain this energy balance. Stars that gain too much speed get slowed down by gravitational encounters. Slow stars get accelerated. This self-regulating process ensures that merged galaxies settle into stable configurations. The virial theorem acts like an invisible cosmic accountant maintaining perfect energy equilibrium. What happens to the beautiful spiral patterns of merging galaxies? They get completely scrambled through a process called orbital mixing. This phenomenon destroys all traces of the original galactic architecture. Orbital mixing occurs when gravitational interactions randomize stellar orbits. Stars that once followed orderly circular paths around their galaxy's center get scattered onto elliptical and highly inclined orbits. Imagine stirring cream into coffee. The organized swirls gradually disappear as the mixing process creates a uniform blend. Galaxy mergers do something similar to stellar orbits. The spiral arms that once defined both galaxies dissolve completely. Stars that were part of organized spiral patterns become randomly distributed throughout the merged system. This mixing process takes several 100 million years to complete. By the end, no remnant of the original spiral structure remains visible. The result creates the smooth, featureless appearance characteristic of elliptical galaxies. Galaxy mergers don't happen instantly. The gravitational interactions require time to redistribute energy among all stellar participants. Astronomers sometimes describe this settling timeline using something called the relaxation time. Relaxation time describes how long gravitational interactions need to smooth out the energy distribution. During this period, fast-moving stars gradually slow down while slow stars speed up. The process works through countless gravitational encounters. Each time stars pass near each other, they exchange momentum and energy. High-energy stars give some energy to low-energy stars. After many such encounters, the entire stellar population reaches what physicists call thermal equilibrium. All stars settle into a smooth distribution of velocities and energies. For typical galaxy mergers, this settling process can take around 1 billion years. This represents a significant fraction of cosmic time, but it's brief compared to the merged galaxy's total lifetime. The relaxation process creates the stable, long-lived elliptical galaxies we observe throughout the universe. Why do some merged galaxies end up round while others become football-shaped? The answer depends on how angular momentum gets redistributed during the collision. This process determines the final galaxy's overall shape and rotation pattern. Angular momentum describes rotational motion. Every star orbiting within a galaxy carries angular momentum based on its speed and distance from the center. During galaxy mergers, gravitational torques transfer angular momentum between different stellar populations. Some stars gain rotational energy while others lose it. The final distribution of angular momentum determines whether the merged galaxy rotates rapidly or slowly. Fast rotation creates a flattened, football-shaped galaxy. Slow rotation produces a nearly spherical system. Most galaxy mergers reduce the total angular momentum compared to the original spiral galaxies. The gravitational interactions tend to cancel out organized rotation, creating slowly spinning elliptical systems. This explains why elliptical galaxies typically rotate much more slowly than the spiral galaxies that formed them. Merged galaxies develop a distinctive two-zone structure with a dense central core surrounded by an extended halo. This architecture results from the different ways that various stellar populations respond to gravitational interactions. The core forms when stars lose orbital energy and settle into tight central orbits. These stars become gravitationally bound to the innermost regions of the merged system. Meanwhile, other stars gain energy and migrate to large orbital distances. These outlying stars form what astronomers call the galactic halo. They remain gravitationally connected but orbit far from the central concentration. The boundary between core and halo creates a sharp transition in stellar density. The core contains most of the galaxy's mass packed into a relatively small volume. The halo spreads the remaining stars across a much larger region. This two-zone structure represents a fundamental characteristic of elliptical galaxies. The central concentration provides gravitational stability, while the extended halo contains the galaxy's outer envelope. The core halo architecture can persist unchanged for many billions of years after the merger completes. Do stars move faster or slower after their galaxies merge? Surprisingly, they move faster on average, but in more random directions. This phenomenon is called gravitational heating, and it increases what astronomers measure as velocity dispersion. Velocity dispersion describes how much stellar speeds vary around the average value. Low dispersion means most stars move at similar speeds. High dispersion indicates a wide range of different velocities. Gravitational heating works like shaking a box of marbles. The interactions between stellar orbits add energy to the system. This extra energy gets converted into increased random motion. Individual stars don't necessarily move faster after heating, but their velocity vectors point in more varied directions. The organized circular motion of spiral galaxies gets converted into chaotic elliptical orbits. Higher velocity dispersion actually creates greater gravitational stability. The increased random motion helps the galaxy resist disruption from external gravitational influences. Merged galaxies end up with velocity dispersions several times larger than their spiral galaxy ancestors. This gravitational heating represents one of the most important outcomes of the merger process. Gas clouds floating peacefully between stars suddenly face enormous pressure during galaxy collisions. This compression pushes them beyond a critical density threshold. Once they cross this line, gravity takes over completely. Imagine squeezing a sponge filled with water. At first, nothing happens, but squeeze hard enough and water starts gushing out. gas clouds work similarly under gravitational pressure. The critical threshold is called the Jeans instability limit. Below this density, gas pressure balances gravity and the cloud remains stable. Above this limit, gravity overwhelms gas pressure and the cloud collapses. During galaxy mergers, shock waves compress vast regions of interstellar gas simultaneously. Multiple clouds reach the collapse threshold at the same time across enormous volumes. This creates conditions for massive star formation episodes that can last for millions of years. The universe transforms quiet galactic neighborhoods into bustling stellar factories. Something extraordinary happens to the space between stars during galaxy collisions. Shock waves ripple outward from the collision zone. These are not sound waves, but pressure disturbances that completely reorganize the interstellar medium. The interstellar medium consists of gas and dust floating in the vast spaces between stars. Under normal conditions, this material drifts slowly and quietly through space. Shock waves change everything. They compress the interstellar medium to many times its normal density. They heat the gas to extreme temperatures. They trigger chemical reactions that normally happen very slowly. Picture a calm lake suddenly hit by a speedboat. Waves spread outward, churning up sediment and disturbing everything in their path. Galactic shock waves do something similar to interstellar space. These disturbances create the perfect trigger conditions for star formation. Compressed gas begins collapsing under its own gravity. What was once empty space becomes crowded with stellar nurseries. The shock wave effect can propagate across entire galaxies, transforming their star formation activity completely. Normal galaxies create new stars at a steady, predictable pace. Galaxy collisions shatter this calm routine. They trigger what astronomers call starburst events that multiply star formation rates by incredible factors. A typical spiral galaxy like our Milky Way forms about one new star per year. During a starburst, that rate can increase tenfold or even 100-fold. The starburst phenomenon happens when collision shock waves compress enormous amounts of gas simultaneously. Instead of gradual sporadic star birth, entire regions ignite at once. These events create some of the brightest objects visible across cosmic distances. Starburst galaxies outshine normal galaxies by tremendous amounts. They become cosmic beacons detectable from billions of light years away. The intense activity does not last forever. The available gas gets consumed relatively quickly. But during peak starburst periods, these galaxies produce more stars in a few million years than normal galaxies create in billions. Galaxy collisions transform sleepy cosmic neighborhoods into blazing stellar factories operating at maximum capacity. Where do the universe's most massive stars come from? They require special conditions that only occur when giant molecular clouds smash into each other during galaxy mergers. Giant molecular clouds are the largest structures of gas in galaxies. These cosmic clouds can contain millions of times more material than our Sun. Under normal circumstances, they form stars slowly and inefficiently. Cloud collisions change this completely. When two giant molecular clouds crash together, they create ultra-dense cores with incredible gravitational pull. These cores contain enough material to form stars dozens of times more massive than our Sun. Think of it like two snowballs colliding and sticking together. The combined mass creates a much larger, denser object than either original snowball. Massive stars form only in these dense collision zones. They require enormous amounts of raw material concentrated in small regions. Normal star formation processes cannot gather enough matter quickly enough. These stellar giants burn incredibly hot and bright. They live fast and die young in spectacular supernova explosions. But during their brief lives, they dominate their cosmic neighborhoods with intense radiation and stellar winds. Does turbulence help or hurt star formation? Surprisingly, the chaotic gas motions created during galaxy collisions actually improve star formation efficiency. This turbulent energy helps overcome the forces that normally prevent stellar birth. Turbulence describes chaotic, swirling motions in gas. Picture cream being stirred into coffee. The swirling patterns represent turbulent flow on a small scale. In galactic gas clouds, turbulence creates density variations. Some regions become compressed while others expand. The compressed zones provide ideal conditions for gravitational collapse. Without turbulence, gas clouds often remain too uniform to collapse. They need density concentrations to get the star formation process started. Turbulent motions naturally create these concentration points. Galaxy collisions inject enormous amounts of turbulent energy into interstellar gas. The chaotic motions help break up large clouds into smaller, denser fragments that can collapse more easily. Higher turbulence levels lead to more efficient conversion of gas into stars. This explains why merging galaxies often show dramatically increased star formation rates compared to isolated systems. Magnetic fields normally act like invisible brakes on star formation. They prevent gas clouds from collapsing as quickly as pure gravity would predict. Galaxy collisions disrupt these magnetic barriers and accelerate stellar birth. Magnetic field lines thread through interstellar space like invisible wires. Gas particles must follow these field lines as they move. This constraint slows down the collapse of gas clouds toward dense stellar cores. Think of magnetic fields like guidelines that keep crowds moving in organized lines. The guidelines prevent rapid, chaotic movement even when people want to rush forward. During galaxy mergers, gravitational forces stretch and compress these magnetic field lines. The organized field structure gets tangled and weakened. Gas particles gain more freedom to move toward gravitational concentration points. Field line compression actually helps star formation in some regions. Squeezed magnetic fields can pinch gas clouds and accelerate their collapse. The reorganized field structure removes barriers that normally slow stellar birth. This magnetic field disruption represents another way that galaxy collisions accelerate star formation beyond normal rates. Galaxy collisions do not just create more stars, they also improve the conditions for planet formation around those stars. This happens through a process called metal enrichment that mixes heavy elements throughout both galaxies. Astronomers use the term metals to describe all elements heavier than hydrogen and helium. These include carbon, oxygen, silicon, and iron. Planets form primarily from these heavier elements. Older stars create heavy elements through nuclear fusion in their cores. When these stars explode as supernovas, they scatter heavy elements into space. Normally, this enrichment happens slowly and unevenly. Galaxy collisions speed up and thoroughly mix this enrichment process. The gravitational interactions stir together gas from different regions of both galaxies. Areas that were metal poor suddenly become metal rich. Higher metal content makes planet formation much more efficient. Rocky planets like Earth require substantial amounts of heavy elements. Gas giants need solid cores made of metals and rock. Stars born during galaxy mergers often have access to more heavy elements than stars forming in isolated galaxies. This creates better conditions for diverse planetary systems. Massive stars created during galaxy collisions do not just burn brightly. They explode as supernovas that trigger even more star formation. This creates a chain reaction that can propagate across entire galactic regions. Supernovas are among the most energetic explosions in the universe. When a massive star runs out of fuel, it collapses and then explodes with incredible violence. The explosion sends shock waves racing outward at thousands of miles per second. These supernova shock waves compress nearby gas clouds, just like the original collision shock waves did. Compressed clouds reach the gravitational collapse threshold and begin forming new stars. Some of these new stars are also massive enough to eventually explode as supernovas. Their explosions trigger additional rounds of star formation. The process can continue for millions of years. Picture dominoes falling in sequence. Each supernova explosion knocks over the next group of star formation regions. The chain reaction spreads throughout the galaxy like a slow-motion fireworks display. This feedback process explains why galaxy collisions can maintain elevated star formation rates for extended periods. The initial collision shock waves start a self-sustaining cycle of stellar birth and death. Newly formed massive stars do not just shine brightly, they create expanding bubbles of hot gas called H2 regions. These bubbles act like cosmic bulldozers, compressing surrounding material and triggering additional star formation. H2 regions form when intense ultraviolet radiation from hot stars ionizes nearby hydrogen gas. Ionization strips electrons from hydrogen atoms, creating a plasma of charged particles. This ionized gas heats up to extreme temperatures and begins expanding rapidly. The hot plasma pushes against cooler, denser material surrounding the star. This creates an expanding shell of compressed gas. Think of inflating a balloon inside a box of sand. The balloon pushes outward, compacting the sand against the walls. H2 regions work similarly, compressing interstellar gas into dense shells. These compressed shells often become unstable and fragment into smaller clouds. Each fragment can then collapse to form new stars. One massive star can trigger the formation of dozens of smaller stars through this process. During galaxy collisions, thousands of massive stars form simultaneously. Their expanding H2 regions create a complex network of compression zones throughout both galaxies. How much of a galaxy's gas actually gets converted into stars? Under normal conditions, the conversion rate stays quite low. Galaxy collisions dramatically increase this star formation efficiency, converting much larger fractions of available gas into stellar material. Star formation efficiency measures what percentage of a gas cloud's mass becomes stars. In isolated galaxies, this efficiency typically ranges from 1 to 5%. Most gas remains unconverted. Multiple factors normally limit conversion efficiency. Gas clouds disperse before they can fully collapse. Stellar winds blow away remaining material. Only small fractions of the original cloud mass end up in stars. Galaxy collisions change this equation completely. The shock wave compression and gravitational disruption overcome many normal limiting factors. More gas reaches the density thresholds needed for star formation. Enhanced turbulence breaks large clouds into smaller fragments that collapse more efficiently. Magnetic field disruption removes barriers to gravitational collapse. The combined effects can increase conversion efficiency to 20 or 30%. This efficiency boost explains why merging galaxies can exhaust their gas supplies relatively quickly during intense starburst phases. Much more gas gets converted to stars in much shorter time periods. Galaxy collisions do not just create individual stars. They also form some of the universe's most densely packed stellar communities. These are called globular clusters, and they contain hundreds of thousands of stars crowded into relatively small volumes. Globular clusters are among the oldest structures in galaxies. They form when extremely dense gas concentrations collapse all at once. The result creates tightly bound groups of stars that stay together for billions of years. Normal star formation rarely creates such dense stellar associations. It typically produces loose groups or individual stars scattered across large regions. Globular cluster formation requires very special conditions. Galaxy collisions provide these special conditions. The extreme compression during mergers can squeeze gas to densities far beyond normal thresholds. When these ultra-dense regions collapse, they form massive stellar clusters. Picture a crowd of people being squeezed into an elevator. Everyone gets packed much more tightly than they would choose voluntarily. Globular clusters represent stellar populations squeezed together by cosmic forces. These dense stellar communities can survive intact for the entire age of the universe. They serve as fossil records of the intense star formation conditions during ancient galaxy mergers. What happens when thousands of stars form simultaneously in the same region? They begin their evolutionary journeys together, creating what astronomers call stellar populations. These synchronized groups reveal important information about cosmic star formation history. Stellar populations are groups of stars that formed at the same time from the same gas cloud. They share similar ages and chemical compositions, but they have different masses, which means they evolve at different rates. Massive stars evolve quickly and die young in supernova explosions. Medium-mass stars like our Sun evolve slowly over billions of years. Low-mass stars evolve so slowly they remain essentially unchanged. During galaxy collisions, intense star formation episodes create enormous stellar populations all at once. Entire regions of both galaxies become populated with stars of the same age but different masses. These populations provide cosmic laboratories for studying stellar evolution. Astronomers can observe stars at different evolutionary stages within the same population. It is like watching different people age at different rates within the same generation. The synchronized formation during galaxy mergers creates some of the largest and most diverse stellar populations in the universe. They represent the ultimate cosmic construction projects that build stellar communities through apparent destruction. The universe began with tiny ripples in density scattered throughout space. These weren't random variations, but the seeds that would grow into every galaxy we see today. Small structures always formed first in this cosmic construction project. Density fluctuations are regions where matter clumped slightly more or less than average. Think of them like gentle hills and valleys in an otherwise flat landscape. Gravity amplified these small differences over billions of years. The early universe contained no galaxies, no stars, no complex structures at all. Just hydrogen and helium gas with these subtle density variations. But gravity never stops working. It pulls matter from low-density regions toward high-density concentrations. This process follows a strict hierarchy. The smallest concentrations collapse first because they need less time to overcome gas pressure. Larger structures form later as smaller ones merge together. Over cosmic time, this bottom-up construction built everything from star clusters to galaxy superclusters. The universe assembles its architecture through step-by-step growth, not sudden appearance. Can tiny dwarf galaxies really grow into massive galactic giants? The answer reveals one of cosmology's most important principles. Large structures form by merging smaller structures, not by growing in isolation. Bottom-up structure formation describes how the universe builds its architecture. Small objects form first, then merge to create progressively larger systems. It's like assembling a skyscraper from individual bricks, rather than casting the entire building at once. Dwarf galaxies were among the first galactic structures to form in the early universe. These small systems contain just millions or billions of stars. They seem insignificant compared to massive galaxies like our Milky Way. But appearances deceive. Today's giant galaxies resulted from countless mergers between these early dwarf systems. Each collision added mass and complexity to the growing structure. Computer simulations track this hierarchical growth over cosmic time. They show how dozens of dwarf galaxy mergers can build a single massive galaxy. The process requires billions of years, but follows predictable patterns. This bottom-up assembly explains why massive galaxies appear only in the recent universe. The early cosmos contained only small building blocks that hadn't had time to merge yet. Why do small galaxies become rarer over cosmic time while large galaxies become more common? This transformation reflects the ongoing merger process that redistributes galactic mass across the universe. The galaxy mass function describes how many galaxies exist at different mass ranges. It's like a census that counts galaxies by weight instead of location. This census changes dramatically over cosmic history. In the early universe, small galaxies vastly outnumbered large ones. The mass distribution was heavily skewed toward low-mass systems. Giant galaxies were extremely rare. Today's universe shows the opposite pattern. Small galaxies have become much rarer while intermediate and large galaxies dominate the census. The mass distribution shifted upward over billions of years. This shift happens because small galaxies get consumed during mergers. Two small galaxies combine to create one larger galaxy. The total mass stays the same, but the number of individual systems decreases. The mass function evolution provides direct evidence for hierarchical structure formation. It demonstrates how the universe redistributes matter from many small objects into fewer large objects through mergers. Every massive galaxy has a family tree that traces its ancestry back through cosmic time. Astronomers call this genealogical map a merger tree. It reveals how countless smaller galaxies contributed to building today's galactic giants. A merger tree looks like an upside-down family tree. At the bottom, you start with many small ancestral galaxies. Moving upward through time, these branches merge together into progressively fewer and larger trunks. Each merger event represents a marriage between two galaxy lineages. Their combined mass and stellar populations create a single larger descendant. That descendant can then merge with other galaxies to create even larger systems. Computer simulations generate these merger trees by tracking dark matter structure formation over cosmic history. They follow every halo from its initial formation through all subsequent merger events. The trees reveal fascinating patterns. Some galaxies result from many small mergers over long time periods. Others form through a few major collision events. Each path creates galaxies with different properties and stellar populations. Merger trees help astronomers understand why galaxies look the way they do today. They connect present-day observations to the complex merger histories that shaped galactic evolution. Large galaxies don't just collide with equals. They also gradually consume smaller satellite galaxies that orbit around them. This ongoing absorption process allows massive galaxies to grow continuously over cosmic time. Satellite galaxies are smaller systems gravitationally bound to larger hosts. Our Milky Way has dozens of these galactic companions orbiting at various distances. The largest satellites contain billions of stars, while the smallest have just thousands. The absorption process happens slowly but inexorably. Tidal forces from the host galaxy gradually strip stars away from satellite systems. The satellite's orbit decays as it loses mass and energy. Think of a small moon gradually spiraling into a massive planet. Gravitational forces stretch and distort the satellite until it eventually merges with its host. Galaxy absorption works through similar mechanisms. This process can take several billion years to complete. During this time, satellite galaxies lose most of their stars to the host galaxy's outer regions. Only the central cores might survive to reach the galactic center. Satellite absorption explains how massive galaxies continue growing even after major merger episodes end. They maintain steady growth rates by consuming their smaller neighbors. What happens to small galaxies when they venture too close to massive neighbors? They get torn apart by tidal forces that stretch them into long streams of stars scattered across space. Tidal disruption occurs when gravity pulls harder on the near side of an object than the far side. This differential force stretches the object until it breaks apart completely. Ocean tides work through the same mechanism on a much smaller scale. Small galaxies experience tidal disruption when they pass through the outer regions of massive galaxy halos. The gravitational force difference across the small galaxy's diameter becomes strong enough to overcome its internal gravity. The disruption creates spectacular stellar streams that can stretch across millions of light years. These streams mark the gravitational trail of destroyed galaxies like cosmic breadcrumbs leading back to the disruption site. Astronomers have discovered dozens of these stellar streams around nearby massive galaxies. Each stream represents the fossil remains of a satellite galaxy that wandered too close to its massive neighbor. The streams provide direct observational evidence for ongoing galaxy cannibalism. They show that hierarchical growth continues in the present universe, not just the distant past. Galaxy mergers don't just redistribute stars and gas. They also mix and concentrate the heavy elements that earlier stellar generations created. This enrichment process improves conditions for planet formation throughout the merged system. Heavy element enrichment, called metallicity by astronomers, measures how much carbon, oxygen, silicon, iron, and other complex elements a region contains. These elements are essential for rocky planet formation and potentially for life. Stars create heavy elements through nuclear fusion in their cores. When massive stars explode as supernovas, they scatter these elements throughout their surrounding regions. But this enrichment happens slowly and unevenly in isolated galaxies. Galaxy mergers accelerate and homogenize the enrichment process. The gravitational interactions thoroughly mix gas from different regions of both galaxies. Previously metal-poor areas become metal-rich almost instantly. This mixing process creates more chemically uniform galaxies with higher average metallicity. Stars forming after the merger of access to substantially more heavy elements than their predecessors. Enhanced metallicity represents another way that galaxy destruction actually improves cosmic conditions. The universe builds chemical complexity through these violent mixing events. Do larger dark matter halos always contain more stars? Surprisingly, the relationship between dark matter mass and stellar mass follows remarkably consistent proportions across cosmic time. This correlation suggests that galaxies and their dark matter halos grow together through coordinated evolution. The stellar mass-halo mass relationship compares the visible stars in galaxies to the invisible dark matter that surrounds them. Dark matter halos can be hundreds of times more massive than the stars they contain. This relationship remains surprisingly stable despite billions of years of merger activity. Small halos contain proportionally fewer stars per unit mass. Large halos also show reduced stellar fractions. Medium-sized halos achieve maximum stellar efficiency. The stable proportions suggest that star formation and dark matter growth stay coordinated during merger events. Neither process dominates completely. They maintain balance through complex feedback mechanisms. This coordination likely involves supernova explosions and black hole activity that regulate star formation rates. Too much star formation triggers feedback that shuts down further stellar birth. Too little allows continued gas accumulation. The relationship provides crucial constraints for understanding galaxy formation. It shows that visible and invisible matter evolution remain fundamentally connected throughout cosmic history. Do galaxies merge more frequently in crowded cosmic neighborhoods? The answer reveals how environment dramatically influences galactic evolution. Dense regions experience far more merger activity than sparse cosmic voids. Environmental dependence describes how galactic properties change based on local cosmic density. Some regions of the universe contain many galaxies clustered together. Others remain nearly empty of galactic structures. Galaxy clusters represent the densest cosmic environments. These regions can contain thousands of galaxies packed into relatively small volumes. The high density creates frequent gravitational encounters between neighboring systems. In contrast, cosmic voids contain very few galaxies separated by enormous distances. Galaxies in these sparse regions rarely encounter neighbors close enough for merger events. Statistical studies confirm that merger rates increase dramatically with environmental density. Cluster galaxies merge dozens of times more frequently than isolated void galaxies. This environmental effect helps explain why galaxy populations differ between dense and sparse cosmic regions. Crowded areas contain more massive, elliptical galaxies formed through mergers. Sparse regions preserve more original spiral galaxy populations. When were galaxy mergers most common in cosmic history? The answer lies in measuring merger rates at different redshifts. This analysis reveals that the early universe experienced far more collision activity than today's cosmos. Redshift measures how much the universe expanded while light traveled from distant galaxies to our telescopes. Higher redshift observations show galaxies as they existed billions of years ago. Lower redshift observations reveal more recent galactic states. Merger rate studies consistently find that collision frequency was much higher in the past. The early universe experienced merger rates 10 times higher than current levels. Nearly every galaxy participated in major collision events. This trend makes perfect sense from a hierarchical structure formation perspective. The early universe contained more small galaxies in closer proximity. Higher cosmic density led to more frequent gravitational encounters. As the universe expanded and matured, merger rates declined steadily. Galaxies became more isolated as cosmic expansion increased distances between them. The largest systems had already formed through earlier merger events. Today's low merger rates represent the mature phase of cosmic structure formation. Most hierarchical assembly occurred billions of years ago when conditions favored frequent galaxy interactions. How do astronomers know that today's galaxies formed through ancient mergers? They examine galactic morphology for fossil evidence of past collision events. These structural signatures persist for billions of years after merger completion. Galactic morphology describes a galaxy's overall shape, structure, and appearance. Different formation histories leave distinctive morphological signatures that trained astronomers can recognize and interpret. Elliptical galaxies show the clearest merger signatures. Their smooth, featureless appearance results from thorough orbital mixing during collision events. The original spiral structures of their progenitor galaxies disappeared completely. Many elliptical galaxies also contain stellar shells and streams in their outer regions. These features represent the fossil remains of smaller galaxies that were tidally disrupted during past merger events. Even some spiral galaxies preserve evidence of ancient encounters. Warped disks, off-center bulges, and peculiar stellar distributions often indicate past gravitational interactions with neighboring systems. Advanced computer simulations can reproduce these observed morphological features by modeling specific merger scenarios. This allows astronomers to reconstruct the collision histories that created today's galactic zoo. The morphological evidence provides direct confirmation that hierarchical merger theory correctly describes galactic evolution. Today's universe preserves the architectural signatures of cosmic construction through collision. Most of every galaxy consists of matter you cannot see. Dark matter halos surround and dwarf the visible stars in mass by enormous factors. These invisible structures control everything about how galaxies move and merge. Dark matter makes up roughly 85% of all matter in the universe. It doesn't emit light, absorb light, or interact with normal matter except through gravity. Scientists detect its presence only through its gravitational effects on visible objects. Every galaxy sits embedded within a much larger dark matter halo. Think of the visible galaxy as a small island floating in an invisible ocean. The ocean contains far more material than the island, but you can only see the land above water. Our Milky Way's visible stars total about 100 billion solar masses. The dark matter halo surrounding these stars contains over 1 trillion solar masses. That's 10 times more invisible matter than visible matter. This mass ratio means dark matter gravity dominates galactic behavior completely. The visible stars respond to gravitational forces created primarily by invisible material. Dark matter halos determine when, how, and why galaxies merge with each other. What controls the timing and outcome of galaxy collisions? Computer simulations tracking millions of dark matter particles revealed a surprising answer. Dark matter halo mergers drive galaxy mergers, not the reverse. In-body simulations follow the gravitational interactions between enormous numbers of particles over cosmic time. These computer models can track individual dark matter particles as they cluster and merge into larger structures. The simulations revealed that dark matter halos merge first. Only after their invisible frameworks combine do the embedded galaxies begin their collision process. The visible merger represents just the final stage of a much longer invisible process. Picture two soap bubbles approaching each other in slow motion. First, their outer boundaries touch and begin merging. Only later do any objects floating inside the bubbles come into contact. Galaxy mergers work similarly. Dark matter halos extend much farther from galactic centers than visible stars. When two galaxies approach each other, their dark matter halos overlap and begin interacting long before the visible components show any effects. This discovery revolutionized astronomers' understanding of galaxy evolution. The invisible universe drives the visible universe's behavior in ways that cannot be observed directly. Why don't galaxies just bounce off each other when they collide? A process called dynamical friction prevents escape by steadily draining energy from orbital motion. This invisible break ensures that approaching galaxies eventually merge completely. Dynamical friction occurs when massive objects move through environments filled with smaller particles. The moving object gravitationally attracts particles from behind while repelling particles in front. Think of a large ship moving through water filled with floating debris. The ship pulls debris along behind it while pushing debris aside in front. This creates drag that gradually slows the ship's motion. Dark matter halos experience similar friction when they pass near each other. Each halo contains billions of invisible particles that create drag on the other halo's motion. The friction removes orbital energy from the system. As orbital energy decreases, the two halos spiral closer together instead of flying apart. The process takes hundreds of millions of years, but it inexorably drives the halos toward merger. Without dynamical friction, most galaxy encounters would result in brief interactions followed by permanent separation. Friction ensures that close approaches lead to complete mergers that reshape cosmic structure. How does dark matter redistribute itself during halo mergers? The process follows predictable patterns that create what astronomers call NFAW density profiles. These profiles describe how dark matter concentration varies from center to edge. A density profile maps how much matter exists at different distances from a halo's center. Most dark matter halos show similar density patterns despite their different formation histories and merger experiences. The NFAW profile, named after its discoverers, describes a specific mathematical relationship. Dark matter density decreases smoothly from center to edge following a precise formula that fits most observed halos. During merger events, the original density profiles of both halos get disrupted and reformed. The gravitational interactions mix and redistribute dark matter particles throughout the combined volume. The final merged halo settles into a new NFAW profile that reflects its total mass and formation history. Central regions develop steep density cusps where dark matter concentrates most strongly. This profile evolution creates the invisible architecture that will control the merged galaxy's future behavior. The reshaped dark matter distribution determines orbital speeds, stability, and susceptibility to further mergers. Can smaller dark matter structures survive being absorbed by larger ones? Many subhalos resist complete destruction during merger events. Their survival explains why massive galaxies retain satellite galaxy populations. Subhalos are smaller dark matter concentrations that become embedded within larger host halos during merger processes. They represent the dark matter frameworks of satellite galaxies that avoided complete disruption. Tidal forces from the host halo try to strip away the subhalo's outer regions. But if the subhalo's central density exceeds a critical threshold, its core remains gravitationally bound and survives the encounter. Picture a small, tightly wound ball of yarn being pulled apart by strong hands. The outer layers might unravel, but a dense core resists disruption if it's wound tightly enough. Surviving subhalos provide the invisible scaffolding that maintains satellite galaxies around massive hosts. Without these dark matter frameworks, satellite galaxies would lose their structural integrity and dissolve. The subhalo population within massive halos preserves a fossil record of past merger events. Each surviving subhalo represents a smaller galaxy that managed to avoid complete destruction during the hierarchical assembly process. Do massive dark matter halos cluster more strongly than lightweight ones? This bias effect creates enhanced clustering patterns that shape large-scale cosmic structure. Heavy halos prefer to live in already crowded cosmic neighborhoods. Halo bias describes the tendency for more massive halos to cluster together more strongly than random chance would predict. Massive halos show stronger spatial correlations with each other than smaller halos do. This bias occurs because massive halos form preferentially in regions that were already overdense in the early universe. These regions continue attracting additional matter throughout cosmic time, creating persistent clustering enhancements. Think of how expensive restaurants tend to cluster in upscale neighborhoods. They didn't randomly distribute themselves throughout a city. Instead, they preferentially located in areas that already had characteristics they preferred. Massive galaxy clusters represent the most extreme examples of halo bias. These structures contain dozens or hundreds of massive galaxies concentrated in relatively small cosmic volumes. The bias effect amplifies large-scale structure formation by creating stronger gravitational attractions between already massive systems. This leads to accelerated growth of the most massive cosmic structures. Why do some galaxies spin rapidly while others barely rotate at all? The answer lies in how angular momentum transfers between dark matter halos and their embedded galaxies during formation and merger processes. Angular momentum describes rotational motion. Both dark matter halos and galaxies can possess significant angular momentum that affects their shapes and internal structure. During galaxy formation, interactions between infalling gas and the surrounding dark matter halo transfer angular momentum between components. The efficiency of this transfer determines the final galaxy's rotation rate. Picture a figure skater pulling in their arms to spin faster. Angular momentum conservation means that as the skater's mass distribution becomes more compact, their rotation speed increases. Galaxies undergo similar processes during formation. Merger events can either enhance or diminish galactic angular momentum depending on the relative orientations and masses of the colliding systems. Some mergers create rapidly spinning remnants while others produce slowly rotating ellipticals. The angular momentum transport process creates a fundamental connection between invisible halo properties and visible galaxy characteristics. Dark matter rotation patterns directly influence stellar rotation patterns. What prevents merged galaxies from collapsing into black holes or flying apart completely? Gravitational heating during merger events increases stellar velocity dispersion, creating stable configurations that can persist for billions of years. Velocity dispersion measures how much stellar speeds vary around the average value. Higher dispersion means stars move in more random directions with a wider range of speeds. Gravitational heating occurs when stellar orbits get disrupted by changing gravitational potentials during mergers. Stars gain kinetic energy as they respond to the evolving force fields around them. Think of shaking a jar filled with marbles. The shaking adds energy to the marble motions, causing them to bounce around more vigorously. Gravitational interactions during mergers shake stellar orbits similarly. Higher velocity dispersion creates greater resistance to gravitational collapse. The increased random motion provides pressure that balances inward gravitational forces. This prevents the merged galaxy from becoming gravitationally unstable. The heating process transforms organized orbital motion into randomized motion that supports long-term structural stability. Merged elliptical galaxies achieve equilibrium configurations through this velocity dispersion increase. How do galaxies avoid converting all their gas into stars during merger events? Feedback mechanisms involving star formation and dark matter halo heating create self-regulating cycles that control galactic evolution. Feedback describes processes where the products of star formation affect future star formation rates. When massive stars explode as supernovas, they heat surrounding gas and can halt additional stellar birth. During galaxy mergers, intense star formation episodes inject enormous amounts of energy into the interstellar medium. This energy heats gas throughout both the galaxy and its surrounding dark matter halo. Hot gas becomes much less likely to collapse and form new stars. It can even be expelled from the galaxy entirely if heated sufficiently. This creates a natural brake on runaway star formation. The heating affects dark matter halo properties by changing the distribution of gas within the halo. Less centrally concentrated gas creates different gravitational potentials that influence halo evolution. This feedback coupling creates self-regulating systems where star formation rates automatically adjust based on previous activity. Galaxies develop internal thermostats that prevent extreme evolutionary outcomes. When did a dark matter halo first assemble into its current form? The concentration parameter preserves this timing information in the halo's present-day structure. Early forming halos develop different internal architecture than late forming ones. Concentration measures how centrally concentrated a halo's mass distribution becomes. High concentration means most mass sits near the center. Low concentration indicates more uniform mass distribution. Halos that formed early in cosmic history developed high concentrations because the universe was denser when they assembled. The higher cosmic density created steeper gravitational potential wells during collapse. Late-forming halos assembled in a more expanded universe with lower background density. This created shallower potential wells and more extended mass distributions with lower central concentrations. The concentration parameter acts like a cosmic timestamp that records when each halo reached its mature configuration. Astronomers can estimate formation epochs by measuring present-day concentration values. This formation timing information helps explain why galaxies show such diverse properties despite similar present-day masses. Different formation histories create different halo concentrations, which then influence galactic evolution through gravitational effects. Spiral galaxies entering collision events never emerge looking the same. The elegant curved arms that define their original architecture disappear completely. In their place stands a smooth, featureless elliptical galaxy that bears no resemblance to either original participant. Morphological transformation describes how galaxy shapes change during merger processes. Morphology means the overall form and structure that defines different galaxy types. Spiral galaxies display distinctive flat disks with curved spiral arms extending from central bulges. These organized patterns result from orderly rotation and systematic star formation along the arms. Collision events completely scramble this organized structure. Gravitational interactions randomize stellar orbits that once followed predictable circular paths. The spiral patterns dissolve as stars scatter onto chaotic elliptical trajectories. The final merged galaxy adopts an elliptical morphology. These systems appear as smooth, football-shaped collections of stars with no internal structure or organizational pattern. This transformation represents one of the most dramatic changes possible in cosmic architecture. Billions of years of careful structural organization get erased and replaced during relatively brief merger episodes. Why do young galaxies appear blue while old galaxies look red? The answer reveals how star formation history determines galactic appearance. Galaxy collisions accelerate this aging process by shutting down new star formation and allowing existing stellar populations to mature. Galaxy color depends on the types of stars that dominate the total light output. Blue stars are young, massive, and extremely bright. Red stars are older, less massive, and much dimmer. Active spiral galaxies appear blue because ongoing star formation continuously creates new massive blue stars. These bright young stars overwhelm the light from older red stars. giving the entire galaxy a bluish appearance. Merger events typically halt star formation by disrupting and heating the gas supplies needed for stellar birth. Without new blue stars being created, existing stellar populations age and evolve naturally. As the massive blue stars exhaust their fuel and explode as supernovas, they disappear from the galactic light budget. The surviving older red stars become increasingly dominant in determining overall galaxy color. This color evolution transforms blue star-forming galaxies into red quiescent systems over several billion years. Galaxy collisions compress this natural aging process into much shorter timescales. Galaxies cannot form new stars without adequate gas supplies. Several violent processes during merger events remove this essential raw material. Ram pressure and tidal forces act like cosmic vacuum cleaners that strip interstellar gas away from galactic disks. Ram pressure occurs when galaxies move rapidly through dense environments filled with hot gas. The motion creates a headwind that pushes against the galaxy's own gas content with tremendous force. Think of driving a convertible car at high speed. The wind pressure strips away anything not securely fastened to the vehicle. Ram pressure works similarly on galactic gas that isn't tightly bound by gravity. Tidal forces provide another gas removal mechanism. Strong gravitational fields from neighboring massive objects can pull gas away from galaxy outer regions where gravitational binding remains weak. These stripping processes preferentially remove the gas needed for future star formation while leaving behind the stars that already formed. The galaxy retains its existing stellar population but loses the ability to create new generations. Gas-stripped galaxies evolve passively as their stellar populations age without replacement. This creates the red, quiescent elliptical galaxies that dominate dense cosmic environments. What stops star formation so abruptly in colliding galaxies? Astronomers call this sudden shutdown quenching because it extinguishes stellar birth like water dousing a fire. Multiple mechanisms conspire to halt star formation during merger events. Quenching describes the rapid transition from active star formation to complete stellar birth cessation. Galaxies can shut down star formation rates by factors of hundreds within relatively short time periods. The process works through multiple simultaneous mechanisms. Gas heating raises temperatures beyond the thresholds needed for gravitational collapse. Gas removal eliminates raw material supplies. Turbulent motions prevent organized collapse patterns. Additionally, feedback from newly formed stars can accelerate the quenching process. Massive stars created during merger-triggered starbursts inject enormous amounts of energy into their surroundings through stellar winds and supernova explosions. This feedback energy heats and disperses remaining gas supplies before they collapse into additional stars. The galaxy's own star formation activity becomes self-limiting through these energy injection processes. Quenched galaxies enter passive evolutionary phases where existing stellar populations simply age without replacement. This transition marks the end of active galactic growth through star formation. How do galaxy centers become more prominent during merger events? Collision dynamics preferentially drive material toward galactic cores. This process builds massive central bulges that dominate the post-merger galaxy structure. Central bulges are spherical concentrations of older stars located at galaxy centers. These components contain significant fractions of total galactic mass concentrated in relatively small volumes. Spiral galaxies typically have small bulges surrounded by much more massive disk components. The disk stars outnumber and outweigh bulge stars by large factors in most spiral systems. Merger processes reverse this mass distribution. Gravitational interactions scatter disk stars onto more spherical orbits that populate the central bulge region. Material from both galactic disks gets concentrated toward the merger remnant center. The enhanced bulge component becomes gravitationally dominant in the final elliptical galaxy. Instead of disk-dominated systems, post-merger galaxies become bulge-dominated with minimal remaining disk structure. This transformation creates galaxies with completely different mass distributions than their spiral progenitors. The spherical bulge component provides gravitational stability that allows merged systems to maintain their structure over cosmic time. Organized rotation gives way to chaotic motion during galaxy mergers. Stellar velocity patterns transform from orderly circular orbits into randomly oriented elliptical trajectories. Astronomers measure this change through increased velocity dispersion. Velocity dispersion quantifies how much stellar speeds vary around the average value. Low dispersion indicates most stars move at similar speeds in similar directions. High dispersion means stars exhibit a wide range of speeds and directions. Spiral galaxies show low velocity dispersions because most stars follow orderly circular orbits around the galactic center. These organized rotation patterns create predictable velocity distributions with relatively small spreads. Merger interactions inject gravitational energy that randomizes these orderly motions. Stars gain kinetic energy as they respond to changing gravitational potentials during the collision process. The increased random motion provides pressure support that balances gravitational attraction in the merged system. Higher velocity dispersion creates more stable configurations that resist further gravitational collapse. This transformation from rotation-dominated to dispersion-dominated systems represents a fundamental change in galactic internal dynamics. The chaotic motion patterns characterize elliptical galaxy kinematics. Do merged galaxies display random brightness distributions, or do they follow predictable patterns? Remarkably, most elliptical galaxies obey a universal relationship called the de Vaucouleurs profile. This law describes how brightness decreases from center to edge. Surface brightness measures how much light comes from different regions within a galaxy. Central areas typically appear much brighter than outer regions due to higher stellar concentrations. The de Vaucouleurs profile provides a mathematical formula that predicts surface brightness at any distance from the galactic center. This specific function fits observed elliptical galaxies with remarkable accuracy. The profile describes exponential brightness decline with a particular mathematical form. Most elliptical galaxies follow this same brightness distribution regardless of their total mass, formation history, or environmental conditions. This universality suggests that merger processes create standardized internal structures despite starting from very different spiral galaxy configurations. The gravitational mixing during collisions produces predictable final brightness profiles. The de Vaucouleurs law provides strong evidence that elliptical galaxies form through common merger mechanisms that erase individual histories and create universal structural properties. Three basic properties of elliptical galaxies show surprising correlations with each other. Size, brightness, and internal stellar motions follow a tight mathematical relationship called the fundamental plane. This correlation suggests that galaxy mergers create standardized final products. The fundamental plane relationship connects galaxy effective radius, surface brightness, and central velocity dispersion through a specific mathematical formula. These three quantities cannot vary independently in elliptical galaxies. If you know any two of these properties, The fundamental plane equation accurately predicts the third value. This tight correlation holds across enormous ranges of galaxy masses and formation environments. The relationship indicates that merger processes create elliptical galaxies with standardized internal structures. Despite starting from diverse spiral galaxy configurations, merged systems converge towards similar final states. Think of different cake recipes all producing similar final textures when baked under identical conditions. Galaxy mergers act like standardized baking processes that create predictable final products regardless of initial ingredients. The fundamental plane represents one of the strongest pieces of evidence that elliptical galaxies form through common merger mechanisms. The tight correlations would be impossible if these systems formed through diverse evolutionary pathways. Normal galaxies build up heavy elements slowly over billions of years. Galaxy mergers compress this chemical enrichment process into much shorter timescales. The intense star formation during collision events rapidly increases the abundance of elements heavier than hydrogen and helium. Chemical evolution describes how stellar populations gradually increase their heavy element content over cosmic time. Stars create these elements through nuclear fusion processes in their cores. Under normal conditions, chemical enrichment happens slowly and steadily. Each stellar generation slightly increases the heavy element abundance available for subsequent star formation episodes. Merger-triggered starbursts dramatically accelerate this enrichment timeline. The intense star formation creates enormous numbers of massive stars that evolve quickly and explode as element-producing supernovas. These rapid supernova events flood both galaxies with newly created heavy elements. The chemical composition of star-forming gas changes dramatically within just a few 100 million years. Post-merger stellar populations show much higher heavy element abundances than typical spiral galaxy stars. This chemical signature provides fossil evidence of past merger activity that enhanced element production rates. How do astronomers determine when different stars formed within a galaxy? They measure stellar ages and chemical compositions to create age metallicity diagrams. Galaxy mergers create complex patterns in these diagrams by mixing stellar populations from different formation epochs. Metallicity describes the abundance of heavy elements in stellar atmospheres. Astronomers use this term for all elements heavier than hydrogen and helium, regardless of whether they're actually metals. Normal spiral galaxies show simple age metallicity relationships. Older stars have lower metallicity because they formed when the galaxy contained fewer heavy elements. Younger stars show higher metallicity due to gradual chemical enrichment. Galaxy mergers disrupt these simple patterns by combining stellar populations with different formation histories. Stars from both progenitor galaxies get thoroughly mixed during the collision process. The resulting age metallicity distribution becomes much more complex and scattered. Some old stars show high metallicity if they formed in previously enriched regions. Some young stars show low metallicity if they formed from pristine gas. This chemical mixing creates diagnostic signatures that help astronomers identify galaxies that form through merger processes rather than gradual accretion and evolution. Do galaxies evolve faster in crowded cosmic neighborhoods than in sparse regions? Observations confirm that environmental density dramatically affects evolutionary timescales. Galaxies in dense clusters evolve much more rapidly than their counterparts in cosmic voids. Environmental effects describe how local cosmic conditions influence individual galaxy properties. Some regions of the universe contain hundreds of galaxies packed into relatively small volumes. Others remain nearly empty of galactic structures. Dense environments provide more opportunities for gravitational interactions between neighboring galaxies. Higher galaxy densities create more frequent encounters that can trigger merger events or other evolutionary processes. Additionally, dense regions often contain hot gas that fills the space between galaxies. This intergalactic medium can strip gas away from individual galaxies through ram pressure effects. The combination of increased merger rates and enhanced gas stripping accelerates the transformation from blue star-forming galaxies to red quiescent systems in dense environments. Statistical surveys reveal dramatic differences in galaxy populations between dense and sparse cosmic regions. Dense environments contain primarily old red, elliptical galaxies, while sparse regions preserve more young, blue, spiral systems. Our nearest major galactic neighbor races toward us at incredible speed. The Andromeda Galaxy approaches our Milky Way faster than any human-made object has ever traveled. This cosmic collision course cannot be avoided. Andromeda moves toward us at roughly 250,000 miles per hour. That's about 70 miles every single second. The distance between our galaxies decreases continuously as both systems hurtle through space on intersecting paths. Astronomers discovered this approach by measuring the Doppler shift in Andromeda's light. When objects move toward us, their light waves get compressed and appear slightly bluer than normal. This blue shift reveals Andromeda's motion in our direction. The approach represents one of the few cosmic processes humans can observe in real time. Most astronomical events unfold over millions or billions of years. But Andromeda's motion toward us continues at measurable rates during human lifetimes. Gravity ensures this encounter will eventually culminate in a complete merger. The mutual gravitational attraction between both galaxies makes collision inevitable once they venture close enough to each other. When will our galaxies actually collide? Astronomical calculations predict the first contact will occur approximately 4.5 billion years from now. This timeline represents one of the most precisely predicted future events in cosmic history. The collision scenario unfolds in multiple distinct phases spanning several billion years. First contact happens when the outer regions of both galactic halos begin overlapping and interacting gravitationally. Current computer simulations model the entire encounter from initial approach through final merger completion. These models track millions of individual stars and dark matter particles throughout the collision process. The timeline depends on both galaxies' current velocities, masses, and trajectories. Astronomers measure these properties with increasing accuracy using advanced telescopes and detection methods. 4.5 billion years may seem impossibly distant, but it represents a definite appointment in cosmic time. The collision represents the most significant future event in our galaxy's evolutionary history. What will emerge from our galactic collision? Astronomers have already named the merger product Milkomeda by combining Milky Way and Andromeda. This new elliptical galaxy will dwarf either of its parent systems. Milkomeda formation follows the same merger principles that create all elliptical galaxies. The spiral structures of both parent galaxies will disappear completely. In their place will stand a smooth, featureless elliptical system. The combined mass will exceed 1.5 trillion solar masses. That represents more than double the mass of either original galaxy. Additional mass comes from enhanced star formation triggered by the merger process. Computer simulations show Milkomeda will span roughly 200,000 light-years in diameter. This makes it significantly larger than either the current Milky Way or Andromeda individually. The new galaxy will rank among the most massive systems in our local cosmic neighborhood. Milkomeda will gravitationally dominate the local group of galaxies for billions of years after formation. Will Earth survive our galaxy's collision with Andromeda? Despite the cosmic violence surrounding this merger, our solar system will likely maintain stable orbits throughout the entire process. The solar system sits roughly 26,000 light-years from the Milky Way's center. At this distance, gravitational disruptions from the merger remain relatively mild compared to interactions in the galactic core regions. Stars rarely collide during galactic mergers due to the enormous distances between them. Our Sun has essentially zero probability of directly encountering another star during the Andromeda collision. The solar system may get relocated to a different galactic neighborhood as stellar orbits get redistributed. We might end up closer to or farther from the merged galaxy's center than our current position. Earth's orbit around the Sun will remain unaffected by these galactic-scale gravitational changes. The merger occurs over such vast scales that planetary systems maintain their internal organization throughout the process. How will the collision affect star formation rates in both galaxies? The encounter will trigger the most dramatic episode of stellar birth in our galaxy's history. Gas clouds from both systems will collide and compress, igniting massive star formation bursts. Star formation explosions, called starbursts, occur when galactic gas supplies get compressed beyond normal density thresholds. The Milky Way and Andromeda both contain enormous reservoirs of star-forming gas. During the merger, shock waves will ripple through both galaxies' gas supplies. These compression waves will squeeze gas clouds to densities far exceeding normal star formation requirements. The result will create stellar nurseries throughout both galaxies simultaneously. Regions that remained quiet for billions of years will suddenly blaze with the light of newly formed stars. This starburst activity will temporarily make the merged system much brighter than either original galaxy. The enhanced star formation will consume most available gas supplies within a few 100 million years. Both the Milky Way and Andromeda contain supermassive black holes at their centers. These cosmic monsters will eventually merge into a single, even more massive black hole. The process will create one of the most energetic events imaginable. Our galaxy's central black hole contains roughly 4 million times the mass of our Sun. Andromeda's central black hole weighs approximately 100 million solar masses. Combined, they will create an about 100 million solar mass monster. The black holes won't merge immediately when the galaxies first collide. They will initially orbit each other in a gravitational dance that gradually spirals inward over hundreds of millions of years. As the orbital separation decreases, the black holes will begin emitting gravitational waves. These ripples in space-time will carry away orbital energy, causing the black holes to spiral even closer together. The final merger will release more energy than billions of supernovas combined. This event will briefly outshine the entire rest of the merged galaxy through gravitational wave emission and electromagnetic radiation. What forces the two central black holes to eventually merge rather than orbit forever? Gravitational wave radiation removes energy from their orbital motion. This energy loss causes the orbit to decay until the black holes combine. Gravitational waves are ripples in the fabric of spacetime itself. When massive objects accelerate, they create these waves that propagate outward at the speed of light. Binary black hole systems generate gravitational waves continuously as they orbit each other. The wave emission carries away energy from the orbital motion, just like a spinning top gradually slows down due to friction. As orbital energy decreases, the black holes spiral closer together. This creates stronger gravitational waves that carry away energy even faster. The process accelerates as the black holes approach each other. In the final moments before merger, the black holes will orbit each other hundreds of times per second while emitting incredibly powerful gravitational wave bursts. The energy released during this final plunge is enormous. In terms of power, that brief burst can outshine the rest of the merged galaxy, at least in gravitational waves. Gravitational forces during the merger will pull streams of stars away from both galaxies. These tidal tails will stretch across millions of light years like cosmic ribbons, marking the collision site. Tidal tails form when differential gravitational forces stretch galactic structures beyond their normal boundaries. The side of each galaxy closer to its neighbor experiences stronger gravitational pull than the far side. This force difference creates stretching effects that pull material away from both galactic disks. Long streams of stars get drawn out along the orbital paths of the merging galaxies. Astronomical observations show spectacular tidal tails around many merging galaxy pairs throughout the universe. These features can stretch farther than the original galaxies themselves. Our Milky Way-Andromeda merger will create similar tidal streams extending throughout the local group of galaxies. These stellar streams will persist for billions of years as fossil evidence of the merger event. The tidal tails will gradually disperse as individual stars follow their new orbital paths through the merged system. But initially, they will create some of the most dramatic structures in our local cosmic neighborhood. The elegant spiral arms that currently define both the Milky Way and Andromeda will not survive their collision. Gravitational perturbations will completely disrupt the organized disk structures that maintain spiral patterns. Galactic disk disruption occurs when gravitational encounters randomize the orderly orbital motions that maintain flat, rotating disk structures. Spiral arms exist only in well-organized rotating systems. During the merger, gravitational forces from each galaxy will perturb stellar orbits throughout their neighbor's disk. Stars that once followed circular paths around their galactic center will scatter onto chaotic elliptical trajectories. The disruption process will scatter disk stars throughout much larger volumes than they originally occupied. What were once thin, flat disks will become thick, roughly spherical distributions of stars. This architectural destruction eliminates the conditions necessary for spiral arm formation. The merged galaxy will lack the organized rotation patterns needed to maintain spiral structure. The final Milky galaxy will show no trace of the beautiful spiral patterns that currently characterize both parent systems. Billions of years of careful structural organization will disappear during the merger chaos. Stars throughout both galaxies currently follow roughly circular orbits around their galactic centers. The merger will transform these orderly paths into the randomly oriented elliptical orbits characteristic of elliptical galaxies. Orbital mixing describes how gravitational interactions randomize stellar motion patterns during merger events. The process converts organized rotation into chaotic motion through gravitational encounters. Currently, most stars in both galaxies orbit their centers in roughly the same direction and plane. This creates the flat disk structures and organized rotation patterns that define spiral galaxies. Merger perturbations will scatter stars onto orbits with different orientations, eccentricities, and inclination angles. The resulting orbital distribution will show no preferred direction or organizational pattern. This mixing process erases the rotational signatures that characterize spiral galaxy kinematics. The merged system will display the random motion patterns typical elliptical galaxy stellar populations. The transformation represents a fundamental change from rotation-dominated to dispersion-dominated internal dynamics. Milkomata will maintain stability through random stellar motion rather than organized rotation. Both the Milky Way and Andromeda contain hundreds of globular clusters. These ancient collections of stars will get redistributed throughout the merged galaxy during the collision process. Globular clusters are dense spherical groupings containing hundreds of thousands of old stars. These systems formed early in galactic history and orbit throughout the galactic halo regions. Each galaxy currently hosts roughly 150 to 200 globular clusters distributed in roughly spherical patterns around their galactic centers. The clusters follow elongated orbits that carry them far from their host galaxies. During the merger, gravitational perturbations will alter all globular cluster orbits. Some clusters will gain energy and migrate to larger distances. Others will lose energy and fall toward the merged galaxy's center. The final globular cluster distribution will show no memory of which clusters originally belonged to which galaxy. The population will get thoroughly mixed and redistributed throughout the new galactic halo. This redistribution process will create a larger, more extensive globular cluster system around Milkomeda than either original galaxy possessed individually. The combined cluster population will reflect the merged galaxy's enhanced mass and size. When will the chaos of merger finally end? Computer simulations suggest Milkomeda will reach stable equilibrium approximately 2 billion years after the initial collision begins. Final stabilization requires time for all gravitational interactions to settle into steady-state configurations. Stars need billions of orbital periods to establish stable patterns after merger-induced perturbations. The stabilization timeline depends on how quickly stellar orbits can reach equilibrium through gravitational encounters. Relaxation processes gradually smooth out energy and angular momentum distributions throughout the merged system. During the stabilization period, Milkomeda will slowly evolve from a chaotic post-merger remnant into a mature elliptical galaxy with predictable internal structure and dynamics. The final equilibrium state will represent a completely stable galactic configuration capable of persisting essentially unchanged for many billions of years. Milkomeda will become a permanent fixture of our local cosmic landscape. This stabilization marks the completion of our galaxy's transformation from an active spiral system into a quiescent elliptical galaxy. The process represents the natural endpoint of hierarchical structure formation in our cosmic neighborhood. Hundreds of individual galaxies can become gravitationally bound into single massive structures. These cosmic cities, called galaxy clusters, represent some of the largest organized structures in the universe. They form through countless merger events that accumulate galactic building blocks over billions of years. Galaxy clusters contain anywhere from dozens to thousands of individual galaxy members. Each member galaxy orbits within the cluster's shared gravitational field while maintaining its individual identity. The formation process resembles how cities grow by attracting new residents over time. Small galaxy groups merge to form larger associations. These larger groups then combine with other groups to create massive clusters. Gravity provides the binding force that holds these cosmic cities together. The combined mass of hundreds of galaxies creates gravitational wells deep enough to trap additional galaxies that wander too close. The largest galaxy clusters contain total masses exceeding 1,000 trillion times our Sun's mass. This enormous gravitational influence shapes cosmic structure formation across vast regions of space. These clusters represent the endpoints of hierarchical structure formation. They grow continuously by capturing smaller galaxy groups and individual galaxies from their surrounding cosmic neighborhoods. Beyond individual galaxy clusters lies an even grander architectural pattern. Superclusters connect multiple galaxy clusters through vast filamentary structures that stretch across hundreds of millions of light years. Supercluster networks create what astronomers call the cosmic web. This web consists of dense filaments separated by enormous empty regions called cosmic voids. The filamentary structures channel matter flow throughout the universe. Galaxies and galaxy clusters preferentially form along these cosmic highways while avoiding the empty void regions. Think of the cosmic web like a three-dimensional spider web made of invisible dark matter. Galaxies cluster at the intersection points where multiple filaments meet. The web spans the entire observable universe. Our local group of galaxies, including the Milky Way and Andromeda, belongs to the Virgo supercluster. This structure contains thousands of galaxies organized along filamentary patterns. The supercluster networks represent the largest coherent structures that gravity can create before cosmic expansion overwhelms gravitational attraction. They mark the boundary between organized cosmic architecture and random distribution. Something massive pulls our entire local cosmic neighborhood toward a specific direction in space. Astronomers call this mysterious gravitational influence the Great Attractor. It demonstrates how large-scale structure formation continues in the present universe. The Great Attractor represents a concentration of matter so massive it influences galaxy motion across enormous distances. Our local group, along with thousands of neighboring galaxies, flows toward this gravitational concentration. The phenomenon was discovered by measuring the peculiar velocities of galaxies throughout our cosmic neighborhood. Peculiar velocity describes motion that differs from the smooth cosmic expansion pattern predicted by the Big Bang. All galaxies in our region show systematic motion toward the same area of sky. This coordinated flow suggests an enormous mass concentration lies in that direction, hidden behind our own galaxy's disk. The Great Attractor likely consists of multiple massive galaxy clusters and superclusters aligned along our line of sight. Their combined gravitational influence creates a cosmic traffic pattern that directs matter flow across vast regions. This ongoing infall demonstrates that cosmic structure formation continues today. Large-scale gravitational processes still reshape the universe's architecture on the grandest scales. One particular galaxy cluster has taught astronomers more about cosmic structure formation than almost any other. The Coma cluster contains thousands of galaxies packed into a relatively small cosmic volume. It provides a laboratory for studying how galaxy communities evolve. The Coma cluster sits roughly 320 million light-years from Earth. This distance places it close enough for detailed study, but far enough to show the cluster as it existed hundreds of millions of years ago. Observations reveal a mature cluster containing primarily elliptical galaxies with very little ongoing star formation. The galaxy population appears old and evolved compared to galaxies in less dense environments. The cluster's history involves countless merger events that built its current massive structure. Computer simulations can reconstruct how smaller galaxy groups combined over billions of years to create today's configuration. Studies of coma-like clusters throughout the universe reveal common evolutionary patterns. Dense environments consistently produce similar galaxy populations regardless of location or cosmic epoch. The coma cluster represents the mature endpoint of structure formation. It shows what our local cosmic neighborhood might become after billions of additional years of gravitational evolution. Galaxy clusters don't contain only galaxies. They also trap enormous amounts of hot gas heated to extreme temperatures. This intergalactic medium fills the space between cluster galaxies and outweighs all the visible stars combined. Intergalactic medium heating occurs when matter falls into deep gravitational potential wells created by massive galaxy clusters. The infalling gas accelerates and heats up as gravitational potential energy converts to kinetic energy. Shock waves generated during cluster formation heat the gas to temperatures exceeding 100 million degrees. At these temperatures, the gas becomes completely ionized and begins emitting X-rays. The hot gas remains trapped within the cluster's gravitational well because its thermal velocity cannot overcome the cluster's escape velocity. Even at extreme temperatures, the gas moves too slowly to escape. This heated intergalactic medium contains several times more mass than all the cluster's visible galaxies combined. It represents the largest reservoir of normal matter in galaxy clusters. The hot gas provides crucial evidence for cluster formation mechanisms. Its temperature and distribution reflect the violent gravitational processes that assembled these massive cosmic structures. How do astronomers study invisible gravitational fields around galaxy clusters? They observe the X-ray emission from hot gas trapped within these gravitational wells. The X-ray brightness directly maps the cluster's gravitational potential. X-ray emission occurs when hot electrons in the intergalactic medium collide with atomic nuclei and lose energy. The emission rate depends on both gas temperature and density. Regions with deeper gravitational potential wells trap more gas at higher densities. These zones show enhanced X-ray emission that reveals the cluster's invisible mass distribution. Advanced X-ray telescopes can map cluster gravitational fields with remarkable precision. The X-ray images reveal mass concentrations that cannot be seen through optical observations of galaxies alone. Many clusters show multiple X-ray peaks indicating recent merger activity between smaller subclusters. These features provide direct observational evidence for ongoing hierarchical structure formation. The X-ray observations confirm that galaxy clusters contain far more mass than their visible galaxies suggest. Most cluster mass consists of invisible dark matter that reveals itself only through gravitational effects. Why do the largest galaxies in the universe always sit at the centers of massive galaxy clusters? This phenomenon, called the brightest cluster galaxy effect, reveals how cosmic environment directly shapes galactic evolution. Brightest cluster galaxies represent the most massive individual galaxies in the universe. They typically contain trillions of stars and dominate their cluster's central regions. These giant galaxies form through preferential growth within the cluster environment. Their central locations provide access to continuous streams of smaller galaxies that fall into the cluster core. The process works like a cosmic feeding mechanism. Smaller galaxies that venture too close to the cluster center get disrupted by tidal forces and consumed by the central giant. Additionally, the dense cluster environment strips gas away from infalling galaxies through ram pressure effects. This gas eventually flows toward the cluster center, where it can fuel further growth. brightest cluster galaxies demonstrate how environment determines galactic destiny. Location within cosmic structure hierarchy directly controls individual galaxy evolution and final mass. The universe organizes itself into a striking pattern of cosmic density contrasts. Dense filaments containing galaxies and clusters surround enormous empty regions called cosmic voids. This architecture emerged from tiny density fluctuations in the early universe. Cosmic web architecture develops through gravitational amplification of primordial density variations. Regions that started slightly denser than average attracted additional matter over cosmic time. Meanwhile, regions that started slightly underdense lost matter to their denser neighbors. This created an increasingly pronounced contrast between full and empty cosmic regions. The resulting pattern resembles a three-dimensional sponge with matter concentrated along thin walls and filaments. The empty spaces between these structures can span hundreds of millions of light years. Galaxy formation occurs preferentially along the dense filaments where matter concentrates. The void regions remain nearly empty of galaxies despite their enormous volumes. This cosmic web structure provides the framework for all subsequent galaxy and cluster formation. The web pattern determines where massive structures can grow and where they cannot. What prevents cosmic structures from growing indefinitely large? Dark energy, the mysterious force driving cosmic expansion acceleration, limits how large gravitationally bound structures can become. Dark energy influence becomes increasingly important as the universe expands and ages. This repulsive force counteracts gravitational attraction on the largest scales. Early in cosmic history, matter density exceeded dark energy density. Gravitational attraction dominated and allowed structure formation to proceed efficiently. Today's universe has lower matter density due to cosmic expansion. Dark energy density remains roughly constant, so it now dominates the cosmic energy budget. This transition suppresses further growth of the largest cosmic structures. Galaxy clusters can still merge with neighbors, but supercluster formation has essentially ceased. Dark energy sets an upper limit on gravitationally bound structure sizes. No cosmic structures larger than current superclusters will form in the future universe. How do astronomers reconstruct the merger histories that built today's massive cosmic structures? They search for fossil evidence preserved in the present-day configurations of galaxy clusters and superclusters. Fossil evidence appears in the form of structural asymmetries, subcluster distributions, and galaxy population gradients within massive clusters. These features preserve signatures of past merger events. Computer simulations show that merger signatures persist for billions of years after collision events complete. The gravitational mixing process requires enormous time to erase all traces of previous structure. Asymmetric cluster shapes indicate recent merger activity between previously separate subclusters. Symmetric clusters suggest more ancient formation through gradual accretion processes. Galaxy population studies reveal chemical and age gradients that reflect different formation environments. These gradients preserve information about when different cluster regions assembled. The fossil record demonstrates that today's largest cosmic structures formed through hierarchical merging processes identical to individual galaxy formation. The universe builds its architecture through collisions and mergers across all scales.